school. Now it's Rahman from Minnesota. So he's going to present in a different fashion. I hope you appreciate it.
Muito obrigado. Thank you very much for inviting me, and thank you for coming to my talk. So, since Roland asked for a song and dance, I'll do a little song and dance. Let's think about this game. For those of you who went to Catholic school, Echenique, this is, and since we're in Brazil, this is what the game is about. This is samba, and this is trabalhar. This is samba, and this is trabalhar. These are the payoffs in this game. And of course, what we want is menos samba, mais trabalhar. Menos samba, mais trabalhar, right? What I want to do today is prove a folk theorem, okay, with mediated communication and frequent action. So basically what I want is menos samba, mais trabalhar. Okay, so let's see how we can get it. Okay, so everybody has a common discount factor, delta, okay? And R is the rate of interest, the discount rate, and delta T is the time between interactions, okay? So now, what I'm going to do is I'm going to make this environment as difficult as possible for me. So I'm gonna, in the paper I show that in games with private monitoring, what I'm gonna do is even easier. So I'm gonna make it really hard for me. So we don't see the behavior of players, we only see some public signal, okay, which is even harder for me, okay, as I argue, okay? Okay, and let's say that, this is the flow of payoffs, and this is the drift of some Brownian motion that generates these payoffs. So the way I'm going to do it is I'm going to say, I've got some set omega, which is plus or minus 1, okay, well, so everybody sees a binary signal, all right? So here, you know, everybody sees a binary signal, either plus 1 or minus 1. Okay, every period, the probability that the signal is plus 1 is pk, where k is the number of cooperators. And this probability is 1/2 times 1 plus xk times the square root of delta t. Okay? All right, and then if I add up all the little omega t's over time, I end up with a random walk representation of some Brownian motion, capital XT if you'd like, which is equal to xt minus delta t plus the square root of delta t with probability pk and minus the square root of delta t with probability qk or whatever, 1 minus pk. Okay. So as delta t goes to 0, this random walk representation converges to a Brownian motion whose law is dxt is equal to this drift x of at dt plus Wiener process. All right. So it's the stochastic setup. So we don't see what people actually did. So all right. So everything converges to Brownian motion now. The literature has been very successful in promoting this sort of model among economists or game theorists, okay? A lot of success with big punchlines. For example, Sannikov and Skripich argued that collusion is impossible in a setting like this. Instead of the prisoner's dilemma, we have a Corno oligopoly as a stage game. In the prisoner's dilemma, basically, what they argued is you can't get above the line. Okay? But we're going to try to get above the line. So so they argue that it's too much samba, not enough trabalhar, but I'm going to get menos samba, mais trabalhar. We're going to get all the way up to here. And I'm going to show you how. And basically the problem is this. These people, the literature, they make technical restrictions on the set of equilibria that they consider because it's mathematically useful, but it misses out important behavioral traits that we see out there. Okay? And these are the two behavioral traits that you see out there. Okay? So here's a visual aid. All right? Now think of types of equilibria. All right. I know some of you, if this isn't very familiar, just let it, just let it breeze past you, because it's not. It's just for those of you who find this useful. Okay. Think of public equilibria, where people's strategies are restricted so that you cannot condition your behavior on your private information. For instance, what you actually played yesterday. Okay. So in public strategies, you're not allowed to do that, and private strategies you are. Okay. And then we can think of Nash equilibria, and then we can think of communication equilibria. Equilibria with a mediator or arbitrary communication protocols above and beyond what's available, okay? So we're looking at equilibrium with frequent actions, all right? So here's the literature. That's the summary of the literature, okay? Okay, there's nothing here. Okay? What there is in discrete time, everything fails miserably with frequent actions. Okay? So there's nothing here. Alright? Now, what I'm going to do today is I'm going to invite you to take this journey with me to expand your notion of equilibrium. Let's do this together in 2 steps. First, lemma 1, and then lemma 2. Okay? And here are the 2 behavioral traits that you see out there. Going from public Nash equilibrium to public communication equilibrium, we're going to capture secret monitoring, which you cannot have in public Nash equilibrium. So if you see secret monitoring out there, you know they're not playing that, the perfect public equilibrium of these other guys. All right? So I'll tell you. So this is what I'm going to call the speeding ticket dilemma. And I'll tell you the story in a minute. And then we'll go from public communication equilibrium to private communication equilibrium. And this is what I'm going to call the cypress and the oak tree dilemma. And this is all about infrequent coordination. So if you see infrequent coordination, or, normally what you see is all these undergraduates, they go out with their girlfriends or boyfriends and they have these codependent relationships. And that's why they fail so miserably. That's what I'm going to argue. Okay? So let's start. This is the theorem I want to prove. Well, first of all, let me define something. The folk theorem holds means this, that you can get anything in here, okay? In particular, menos samba mas travaya, okay? As long as players are sufficiently patient. So if it fails, that doesn't hold, okay? So folk theorem fails if and only if x0 equals x1 equals x2. All right? And I'm going to prove it with 2 lemmas. All right? So it's a bold statement, right? Basically captures everything. Because if this condition holds, then you can't see it. Nobody can see anything. So of course you can't get anything. Conversely, if this fails in any way, you can do it. Okay? You can get menos samba mas travaya. All right? So let's start with lemma 1. Okay? So the folk theorem holds in public communication equilibrium if in the monotone case. Okay? If X is monotone, I can get this in public communication equilibrium, which means that a mediator, some disinterested third party, makes recommendations, secret recommendations to players. Then everybody does whatever they want. Then the public signal realizes, and then the mediator publicly announces what was recommended to everybody, and then we take the recursive step. All right? So here's how we do it. Okay? But now in public Nash equilibrium, you're only allowed to have your continuation paths depend on the public signal. But now we're going to allow them to depend on what was recommended. As follows. So what we'll do, it's very easy. Let me just do a little Jackson Pollock for a moment, and then I'll say it in English. Okay, so this is what was recommended, and this is the public signal that was observed. Okay, and this is what happens to continuation payoffs. Okay. Okay, here we go. So what we'll do is this. most of the time, and what we'll do is we'll have, so the mediator recommends to each guy to, for some mu small, greater than 0, 1 minus mu mu, 1 minus mu mu. So I ask you to trabalhar with high probability, and I ask you to dance the samba every so often. And then this is what we're going to do. Okay? So most of the time we're in a stable relationship where everybody's asked to work. All right? But every now and in that case, our continuation values don't change. W is the change in your continuation value. Okay? So we have a stable relationship. But every now and then we enter a secret monitoring regime where some guy is asked to play samba, which is actually doing something good for society, for a change. All right? Well, not for a change. Okay? So he's playing the samba. Okay? And now, all right, if you notice, what happens is, if the signal is high, okay, now our relationship, there's something on the table, right? If the signal goes up, then I pay you, and if the signal goes down, then you pay me. I'm the one who's dancing, okay? And what's the amount? W, okay? So that's the relationship, all right? So why does it work? For those of you who like Star Trek, it's because when we're here, if this guy deviates, he raises the drift. If this guy deviates, he lowers the drift, so you can tell who did it. We have pairwise identifiability, conditional on this action profile. So the thing about these guys that do perfect public Nash equilibrium is they're not allowed to do secret monitoring. Okay, so this is the speeding ticket dilemma. You have the cop on the road. Okay, he's got his speedometer, right? And so, if, in some states, the cop is not allowed to hide behind the bushes. So therefore, if you see the cop, you go slow. If you don't see the cop, you go fast, right? So if you want people to go slow, you have to have a cop there all the time. But if you allow for secret monitoring, you could actually have the cop doing something useful most of the time instead of playing with his gun, right? So this is exactly the gain from having secret monitoring. You save yourself the cost of monitoring. Okay, so let's see how this works in Greek. Okay, so let's show that this works. All right. Suppose you were asked to trabalhar. Okay. So today you get 1 minus 2 mu. Okay, from the payoffs. Okay, if you do what you're supposed to do, and then tomorrow. Okay, with probability mu, 1 minus mu, probability 1 minus mu, the other guys also has to trabalhar, and the terms of our agreement don't change, so we can ignore that state. But with probability mu, we're in the secret monitoring regime, and then W's on the line, right? And W's on the line, and then if news is good, I get W. If news is bad, I pay W. All right, so that's what I get if I cooperate when I was asked to do so. Now, if I choose to defect instead, what happens? Well, today, I get 2 times 1 minus mu, and tomorrow, it's the same story, but with different probabilities, because now nobody's cooperating in the secret monitoring regime. Agreed? Okay? So now, if I mess around with this formula, okay, what I'm going to get is that, delta mu W has to be greater than or equal to 1 minus delta, and I substitute for x, okay, for p, okay, this expression, I get x1 minus x naught times the square root of delta t. Okay, you believe me, it's just a trivial calculation, okay? The point is that it is a trivial calculation. I don't need to wave any yellow books at you to get it, okay? This is part of the pitch, okay? So now, so we're looking at frequent action. So as delta t goes to 0, okay, 1 minus delta over delta is like linear in R and linear in delta t. So we get that W must be greater than or equal to R times the square root of delta t times mu times x1 minus x naught, okay? So that's the deal, all right? Okay, what if you were asked to samba, okay? So of course we need x1 bigger than x naught. What if you're asked to do samba? Well, obviously today you gain from samba than from trabalhar. Everybody knows that. Okay, but tomorrow you do too. Because tomorrow, if you're asked to do samba, okay, if the other guy was asked to do trabalhar, by trabalhar, you only raise the probability of having to pay the worker. Right? So you lose today by deviating, you lose tomorrow by deviating, we're done. But here, notice that I use the fact that x2 is greater or equal to x1. So I use the monotonicity for this. Okay, I'm not going to write it down. Okay? Alright, so we use monotonicity to get this. Now, I'll do a little picture, but maybe, well, I'll try to do it here. I'll do it, let's see, I've got till 40, yeah, 5:40, right? Yeah, okay, so some of you maybe don't know about basic arithmetic, so there's this algorithm of Federico, Levine, and masking for discrete time games. I'll just remind you how it works a little bit. 550? Okay, great. Okay, thank you. So what you do to prove the folk theorem with Federico, Levine, and masking is you take some smooth set W, so it has a twice differentiable boundary, okay? And then you pick, well, let's take a magnifying glass over here. I want to get something that's really close to menos nama mais trabalhar, right? So let's take a magnifying glass of this, and so this is the boundary of W, okay? This is what we do today. Okay, the payoff profile from what we do today. This is our lifetime utility, and this is the continuation payoffs starting tomorrow on. Okay, they're contingent. So here's W. Okay, so the way these guys prove a folk theorem in discrete time is as follows. Let's fix a delta t equal delta bar for a little bit. Okay, now. And this is, this is proportional to 1 minus delta over delta. Okay, so this is like R times delta t, approximately, when delta t is small, okay? And this, since the boundary of W, since it's twice differentiable, it has a second order Taylor series expansion. Again, you remember that from high school? So this is like, if you twist, if you turn your head, this is like the square root of 1 minus delta over delta. So it's like the square root of R delta t. But the payments are proportional, are linear in R. So, okay, so this is proportional to R times the square root of delta bar. Okay, so for fixed delta bar, if the interest rate is low enough, eventually the continuation paths will lie inside this set W that we're trying to self-generate, and we're done. So there's some R bar, some interest rate R bar such that these payments are self-generated, and we did it, okay? I mean, there's a little bit more, but I'll spare you the details. Okay, so now we proved the folk theorem in discrete time. So how do we need one more step for the folk theorem for lemma 1, because it's frequent action, so we have to send delta t to 0 first. So what do we do? Let's do this. So let's say that W bar is equal to the W of delta, is the W that makes this constraint bind for a fixed length of time delta bar. Okay? And now for for even more frequent actions, for any delta t less than delta bar, we're going to say that W of delta t equals W bar times the square root of delta t over delta bar. Okay, this is just a number, okay? And what does this look like? Well, it goes through this point, and it fits like a glove. So we proved the folk theorem with frequent actions, okay? So therefore, we managed to reconcile the speeding ticket dilemma, okay? But so the intuition is, of course, that, you can tell who did it after a deviation. There's some way of figuring this out. But what if you can't? What if you don't have monotonicity? For example, this is 1001. Then you can't do it, right? So this guy raises the drift, this guy raises the drift, this guy lowers the drift, this guy lowers the drift, this guy raises the drift, this guy raises the drift. No matter what anybody does, you can't tell who did it after a deviation. So you have to punish everybody. But the punishment is proportional to the square root of delta t. And any gain that you may have is only proportional to delta t from here. So at some point, the cost is going to become exorbitant. Okay, because you have to punish everybody, and you're just gonna, it's not feasible to sustain cooperation. This is the idea of value burning of Sannikov and Skripich, okay? So here's where the cypress and the oak tree dilemma comes in. So, la sugra is the mother-in-law, is that right? Sogra? Soga? Oh, in Spanish, soga is, So my mother-in-law is from California, and she often likes to tell a story that in the 70s, whenever anybody got married, they'd cite a passage from Khalil Gibran, the prophet. And you know, the poem goes, it's like a warning for couples, newlywed couples. He says, let there be spaces in your togetherness, you know. The columns of the building have to be separate, because if the columns are together, then the ceiling is going to fall. And if the cypress and the oak tree grow too close to each other, they'll grow under each other's shadow. They won't grow as much. All right? So we should build spaces in our togetherness. This is going to be the next trick, okay? This is the cypress and the oak tree dilemma. I'm here till Tuesday. Don't drink and drive. So this is how we're going to do it. And here's another issue that I have with perfect public equilibrium, or the spirit of it, particularly in the case of frequent actions, which is that public equilibrium, you know, I would argue, at least broadly, maybe not specifically, that it's about synchronizing your watches with other people. It's about coordinating your histories so that your histories don't diverge. Okay? But we're expected to synchronize our watches every nanosecond of every day. To me, that seems particularly problematic in games of frequent actions. Why don't we do this instead? Let us build spaces in our togetherness. Instead of synchronizing our watches every nanosecond of every day, let's just meet every Monday morning. Let's just do it once a week. We'll meet at 9:30 in the morning. Someone makes sure that the coffee's hot and the fruit is cut, and that's all we have to do. In fact, it's better. So what we'll do is, as we send delta t to 0, we'll pick a fixed length of calendar time, let's say a week, C, and the period of this block grows as delta t goes to 0 to keep the length of calendar time fixed. Okay? So what we're going to do is this. Now, so let me show you, let me do lemma 2 now. Okay, let's see. So here's lemma 2. Now the Folk theorem still holds if x2 minus x1 is different from x1 minus x0. Now, the previous lemma, if I switch the rows of up and down, the result still holds. With the inequalities reversed, doesn't matter, right? So, okay, so if I prove this, then I'm done. Because the only time when this fails is when these two are equal. All right? But then that's a monotone case. Except when, of course, they're equal to 0. And so, but that I'm forgiven for. Okay? So this is the end. Agreed? All right. So this is how we're going to do it. So without loss, let's say this is bigger. This is how we're going to do it. So, you know, since I'm giving a talk on Brownian motions, I have the, I have the privilege of drawing a squiggly line over here. Okay. All right. So what is this squiggly line? So everybody's selling Brownian motions. So I'm selling more Brownian motions than anybody because I have one for each one of you. Each and every one of you. You want a Brownian motion? Here, you have one. You too, and you too. Everybody has a Brownian motion, okay? So let's say that you're Mr. I or Mrs. I or whatever. So the mediator is going to construct a secret Brownian motion for every player. It's going to be their score. So you have your score, and you have your day of reckoning too, of course, or redemption since we're in Brazil. So at period 0, your score is at 0. Okay, and then in period t, your score goes up a tick with some probability, and it goes down a tick with some probability, okay? So I'm going to say 1 minus Ci of AT omega t and Ci of AT omega t. So what the mediator is doing is creating a Brownian motion for everybody, okay? So your score goes down a tick with this probability, okay? And I'll tell you what that is explicitly. This probability depends on the profile of recommendations to the players that period and whether the signal went up or down that period, okay? And it's given by this, if I can do it. So here's Ci of A omega is equal to 1/2 for every A omega except in the following two cases. So Ci of Ti T minus I plus 1, so this is trabalhar, right? So if everybody was asked to trabalhar and output goes up that period, then your failure probability is 1/2 times 1 minus mu over 1 minus mu, P1 over P2. And Ci of Ti S minus I plus 1 equals 1. I'll explain what this means, okay? So this is a little less than 1/2, and this is more than 1/2, okay? So here's the duality argument. The reason why I picked these probabilities is for the following reason. The first reason is that in equilibrium, now your score has no drift. So you can never say that you're out of the woods. You're never out of the woods yet. All right? And second part is that if you ever deviate, you're only going to lower the drift of your score. All right, so let's see let me prove that now. And yes. And again, well, let's see. So I need I can't talk and erase at the same time. All right. Okay, so again, all we have to do is use Bayes' rule. Okay, I'm not going to wave any yellow books at you. This is stochastic calculus for the people by the people. Okay? So let's do it. Let me call this event that your score goes down by a tick, let's call it FT. Okay? That you failed in period T. Okay? So what's the probability that you fail in period T if you were asked to trabalhar and you did trabalhar and output was high? Alright? So what is that? Well, with probability 1 minus mu, the other guy was asked to work, and then with probability P2, mu's is good, and then with probability 1/2 1 minus mu over 1 minus mu, P1 over P2, you fail, okay? And then with probability mu, the other guy was asked to samba, and so then with probability P1, mu's is good, and then with probability 1, you fail. And then you divide by the conditional probability of plus 1, which is 1 minus mu P2 plus mu P1. All right? Now, if you squint, I'm not going to do it for you, but if you squint, it's very easy to see that this is equal to 1/2. That's why I picked it. Do you see? The things cancel out. Okay? Anybody can do this. The people can do this. Okay? Okay, so in equilibrium, your score has no drift. I exhausted. It went to sleep. All right, thank you. So, all right, so what about, so now I want to argue that by deviating you only lower the drift. So what's the failure probability if you were asked to trabalhar but you decided to dance instead and output is high? Okay? So what's that equal to? Well, it's almost the same, but it's, 1 minus mu times P1, because now only one guy is working when the other guy was asked to work, because you're not working, you're dancing, times 1/2 times 1 minus mu over 1 minus mu, P1 over P2, okay, plus mu P0, divided by 1 minus mu P1 plus mu P0. Alrighty? Now this is a little bit messier. Let's see if I go, I don't know where to go. Okay, so let's go here, let's see. So now if I just mess around with this a little bit, I'm going to get that this is equal to 1/2 times 1 plus mu times P naught P2 minus P1 squared divided by P2 times 1 minus mu P1 plus mu P naught. All right, or like this, sorry. So, so I can just break this up into 2 halves and then I get the 1/2 immediately and then it's just a little bit of a mess. But you believe me, right? Yeah? I didn't do much, right? Okay, now as delta t goes, now we're going to send delta t to 0, okay? So when delta t is really, really, really small, this is approximately, there's stuff, this is about 1/2, this is about 1/2, okay? Now this got some things that are linear in delta t, so just forget that, okay? So this is approximately 1/2 times 1 plus mu times x naught plus x2 minus 2x1 times square root of delta t. Okay, and then this is easy. Again, this, high school kid can do this, all right? So this is the failure drift, the maximal failure drift from a deviation. Okay, so I'm going to call this Z star star because there is a Z star that's coming. Okay? This is the maximal failure drift. All right, but now when you're contemplating a deviation, I know I haven't told you everything, but hopefully by the time we get to the end, all the pieces will add up, I hope. At least that's the promise. So when you're thinking about deviating, and you're thinking about the secret score that you don't know anything about, you don't know what output is going to be that period. So what is going to be, so what you're thinking about is what's the probability that I fail, given that I was asked to work and I decided to samba instead, right? So, it's easy to do this, it's the same calculation, okay? But the point is that it's going to be approximately 1/2 times 1 plus 1/2 times mu x naught plus x2 minus 2x1, okay? Some square root of delta t. Okay, so this, it's a half of this. So this is going to be Z star because it has half as many stars. Okay? All right. Okay. All right, well, I'll do it again. So, of course, now you see where this is coming from, yeah? Because if this condition fails, this collapses. I can't have a drift. I can't have a score that is at the same time secret from you, okay, and reflecting of your behavior okay? Because, so what I'm doing is, you don't know what I recommended to the other guy, okay? But what I recommended to the other guy has nothing to do with you, whether or not you shirked, okay? All right? Now, you see the public signal, and I'm trying to make it secret from you. Okay, but I can't unless I do the following. Unless I make it that you need 2 keys to open a lock. You only have 1 key, which is the output. Okay, but now I make it that you need 2 keys, like in cryptography, and you can't open this lock because you don't know the other guy's recommendation. All right. Maybe I didn't explain clearly why. I have some time, so let's see why. So, in the public world, in the public strategies world, after a bad outcome, you have to punish. And that becomes too expensive because the cost is of order root delta t and the benefit is only of order delta t. But wouldn't it be nice if you didn't punish all the time? If you only punished half of the periods, for example. But if you knew which periods those were going to be, those would be the periods where you would deviate. So, as the mediator, or as the guy who does, as the dynamic mechanism designer, what I want is to keep those periods where I forgive you secret from you, okay? The trouble is that you see the output. I'm not allowed to change the exogenous information structure. But what I'm allowed to do, or what I'm urging you to grant me, is that I can vary the endogenous information structure. Okay, so I keep these recommendations secret from you for a week. Okay, we build spaces in our togetherness, and then we'll use this scoring rule to not punish every time there's a bad outcome. So here we'll have you know what the score is, okay? You know what your score is, and we'll have a cutoff, okay? We'll do a test, okay? So this cutoff is y star star, and it's equal to minus z star star times c. So I'll have a cutoff that's linear in time, because it's easy, you know, let's not complicate what doesn't need to be complicated for now, okay? And then, if you pass the test, if your score is above this cutoff, then you will be forgiven, you know, and your continuation value in the game will not be affected. But if you fail this test, then you'll have to pay some amount W of continuation value. So let's see how big this W must be. All right? So what we'll do first is I'm going to try to discard. So here's my block, okay, of length C. So I'm going to try to argue that this idea is incentive compatible. So first, let's try to discourage a deviation in the first period only. Okay, we have to do that at least. So you're going to deviate it. You're going to samba in the first period when you were asked to trabalhar, and all of the other times you'll be a good person. Okay, you'll do what you're told. Let's suppose. What do you gain? Okay, by doing this? Well, you gain 1 minus delta, so that's the deviation gain, but since delta t is really, really small, you gain approximately r delta t. All right? What do you lose? What you lose is that at the end of the block, W is on the line. Okay? Times, and then your incentive is driven, apart from this, by the change in the probability of punishment associated with your deviation. Yeah? So I can't fit it in here, so I'm going to write it here. Okay? So this multiplies this. All right? If you're a good boy or a good girl, what's the probability of punishment? Well, it's 1 minus phi of z star star times c divided by root c. Because y is a Brownian motion, right? So yic minus yi naught, which is 0, is normal 0c, right? That's the Brownian motion. The variance is proportional to time. And so I have to divide by the standard deviation to get the probability. Do you agree? So that's all it is, right? So it's like times the square root of c. This is the probability that you fail the test. Agreed? Okay, Dixit would be proud. That's all you need. You don't need a yellow book. You just need Dixit. Okay. What if you defect, if you deviate, if you samba instead of trabalhar, what happens? The probability, you change the probability as follows. You have z star star times c minus z star times delta t divided by the square root of c. So for this little length of time, you change the drift by z star, because you haven't seen the output this period yet when you're deviating, right? This is a heuristic argument. The details are there, but anyway. So this is the way to think about it. Okay, now as delta t goes to 0, okay, now let's send delta t to 0, and what do we get? That r is less than or equal to e to the minus rc times w times phi, the derivative, right? Becomes a derivative of z star star root c times z star over root c. Okay, so the way I like to write it is that, I guess we can do this, that W must be greater than or equal to RC times e to the RC divided by phi of z star star root c times z star root c, okay? I'm just messing around with this. See the bound, there's a lower bound on the payment to make it incentive compatible for you not to deviate in the first period only. All right? I got 10 minutes. No? I have 2 minutes? Okay, I can do it.